Hello, my dear friends. Welcome to IKSR chemistry classes. Here we are in lecture number 3 on nuclear chemistry. In this video, we will discuss the nuclear binding energy and its implications in the interpretation of nuclear stability. Let us first of all recapitulate the main points discussed in the previous videos. We have already seen that the observed isotopic mass, that is the actual isotopic mass of an isotope, is always lower than its calculated isotopic mass, that is expected isotopic mass. The calculated isotopic mass of an isotope is always greater than its observed isotopic mass. In other words, the observed isotopic mass of an isotope is lower than its calculated isotopic mass. The isotopic mass of an isotope is calculated by adding the masses of all its constituent particles, while the actual isotopic mass of an isotope is determined experimentally with the help of a spectrometer, mass spectrometer, and it has been given here. The sample is entered into the apparatus through this point. The sample is heated by heater. As a result, the sample vaporizes. Thereafter, the sample is bombarded by a beam of electrons. As a result, the gaseous sample ionizes, which is accelerated by applying electric field. And then magnetic field is applied. As a result, the ionized gaseous sample bend depending upon E/m ratio. The lighter isotope bends to a greater extent, while the heavier isotope having a smaller E/m ratio bends to a lower extent, and thus the isotopes present in the gaseous sample can be detected and their isotopic mass can be determined. The difference between the calculated isotopic mass, that is m, and the observed isotopic mass, that is m dash, of an isotope is called its mass defect. The difference between the calculated isotopic mass and the observed isotopic mass of an isotope is called mass defect. It is denoted by delta m, and therefore delta m can be given by m minus m dash, that is calculated isotopic mass minus observed isotopic mass. Some important terms. We have used the term isotopic mass several times. Now let us define isotopic mass. The mass of one atom of a certain isotope of an element relative to the 1/12th, that is 1/12 of the mass of one atom of C12 isotope of carbon is called its isotopic mass. The mass of one atom of a certain isotope of an element relative to the 1/12th of the mass of one atom of C12 isotope of carbon is called its isotopic mass, and therefore isotopic mass can be given by the following expression. Isotopic mass is equal to mass of one atom of a certain isotope of an element divided by mass of one atom of C12 isotope of carbon multiplied by 12. Let us see an example. The isotopic mass of Cl35 is 34.968852 mu. It must be noted that the isotopic mass is generally fractional due to mass defect. And there is another term, nucleons. The particles present in the nucleus of an atom, that is, protons and neutrons, are collectively known as nucleons, which means nuclear particles. The particles present in the nucleus of an atom, that is, protons and neutrons, are collectively known as nucleons. An atom is given here. These particles are present. Protons and neutrons are present in the nucleus of the atom. And these are nuclear particles, and these are collectively known as nucleons. The number of nucleons, that is the sum of number of neutrons and protons of an atom, is nothing but its mass number. The number of nucleons of an atom is equal to its mass number. For example, the number of nucleons in Cl37 is equal to 37. This is the number of nucleons. That is the sum of numbers of protons and neutrons in the nucleus, and it is nothing but the mass number. The number of nucleons of an atom is equal to its mass number. Transformation of mass into energy. Transformation of mass defect. Transformation of mass defect into energy. The mass defect, that is the decrease or loss in the mass of nucleus or isotope, is transformed into energy in accordance with Einstein's relationship E is equal to mc square. The mass defect, that is the decrease or the loss in the mass of a nucleus or an isotope, is transformed into energy in accordance with Einstein's relationship E is equal to mc square. Here m is the mass which is being transformed into energy, and c is velocity of light, which is equal to 2.99792458 into 10 to the power 8 meter per second. And this formula, this relationship gives 1 AMU is equal to 931.5 mega electron volt. The energy equivalence of 1 AMU is 931.5 mega electron volt. It means if 1 AMU mass is transformed into energy, we will get 931.5 mega electron volt energy. Now, the most important term to be discussed in this video is nuclear binding energy, which is denoted by EB. The energy derived from, it should be FROM, the energy derived from the mass defect, that is delta M, is responsible for holding the nucleons of an atom together, and hence it is called nuclear binding energy, and it is denoted by EB. Let us see it again. The energy which is derived from mass defect, holds the nucleons, that is neutrons and protons of the atom together, and therefore it is called nuclear binding energy. It is denoted by EB. The energy which is obtained by the transformation of mass defect into energy holds the nucleons, that is neutrons and protons of atom together, and therefore it is called nuclear binding energy. We have already seen that 1 AMU is equal to 931.5 mega electron volt, and therefore if delta M AMU, that is mass defect, is transformed into energy, delta M AMU will be equal to delta M into 931.5 mega electron volt. This amount of energy can be derived from the mass defect, and this amount of energy which has been derived from the mass defect is responsible for holding the nucleons together, and it is called nuclear binding energy, which is denoted by EB, and therefore EB is equal to delta M into 931.5 mega electron volt. This is the value of nuclear binding energy. EB is equal to delta M into 931.5 mega electron volt. It is obvious from this expression that greater the mass defect, higher will be the nuclear binding energy. Greater the value of delta M, higher will be the nuclear binding energy, and more stable should be the nucleus. But should be, not will be. More stable should be the nucleus. But it is not exactly true. But it is not exactly true. Let us understand it with the help of an illustrative example. A question has been given for the self-assessment here. State which of the following families is financially more sound. There are three families, A, B, and C, and their income per day in rupees is given here. Family A has income rupees 1000 per day. Family B has income rupees 800 per day, while family C has income rupees 500 per day. On the basis of these data, we can be tempted to conclude that family A is financially more sound, but it is not true. We must consider the number of family members which are supported by this income. Let us see the number of family members in these families. Family A has 5 members, B has 2 members, and C has 3 members. Now let us calculate income per member per day in rupees. It will have rupees 1000 divided by 5, that is rupees 200 per member per day. B has rupees 400 per member per day, and family C has rupees 166.67 per member per day. Now it is obvious that family B is financially more sound and not family A, because we have considered income per member per day. On the basis of this fact, we must be careful. Only on the basis of nuclear binding energy the stabilities of various nuclei cannot be, here cannot be, should not be cannot, only on the basis of nuclear binding energy, the stabilities of various nuclei cannot be compared. This cannot should be omitted. Merely on the basis of nuclear binding energy, the stability of various nuclei should not be compared. The number of nucleons which are to be bound by the given amount of energy must be taken into account. Let us see it again. Not merely only on the basis of nuclear binding energies, the stabilities of various nuclei should not be compared. The number of nucleons which are to be bound by the given amount of energy must be taken into account. In other words, the binding energy per nucleon must be taken, must be considered for comparing the relative stabilities of nuclei. The binding energy per nucleon must be taken into account, must be considered during comparing the relative stabilities of various nuclei. Binding energy per nucleon. The nuclear binding energy available to bind per nucleon of an atom or nuclide is called its binding energy per nucleon. The binding energy, nuclear binding energy, which is available to bind per nucleon of an atom or nuclide is called its binding energy per nucleon. It is denoted by EB bar and given by the following relationship. Binding energy per nucleon is equal to total binding energy divided by total number of nucleons. This binding energy is used to bind such number of nuclear particles, and therefore binding energy per nucleon will be given by binding energy divided by mass number. Mass number is nothing but total number of nucleons. With the help of this expression, binding energy per nucleon can be calculated. Now, time for self-assessment. The isotopic mass of helium-4 is 4.0046 mu. Then calculate its mass defect, nuclear binding energy and binding energy per nucleon. Here is the solution. We have already calculated in lecture number 1 of this chapter that the mass defect of the given He4 nucleus is 0.0303792 mu. This has been calculated already in lecture number 1. And now nuclear binding energy is equal to delta M into 931.5 mega electron volt. Delta M is given here, this one, and multiplied by 931.5 mega electron volt, and the result is 28.298 mega electron volt. And now binding energy per nucleon is equal to nuclear binding energy divided by mass number. Mass number of helium-4 is 4, and on dividing this amount of energy by 4, we get 7.0746 mega electron volt. Each nucleon of He4 nucleus is bound together by this amount of energy. 7.0746 mega electron volt. Binding energy per nucleon and nuclear stability. Greater the binding energy per nucleon, that is EB bar, more stable will be the nucleus, not should be. Greater the value of binding energy per nucleon, more stable will be the nucleus. If we plot EB bar versus the number of different elements, if we plot EB bar versus mass number, if we plot nuclear binding energy per nucleon versus mass number of different elements, first of all, the value of EB bar increases with increase in mass number, attains a maximum value in the range 50 to 70 of mass number and then decreases. If binding energy per nucleon of different elements is plotted against their mass number, first of all, the value of EB bar increases with increase in mass number, then attains a maximum value in the mass number range 50 to 70 and then decreases. For most of the nuclei, the value of EB bar, that is binding energy per nucleon, is about 8 mega electron volt. Most of the nuclei have binding energy per nucleon about 8 mega electron volt. Here we have plotted binding energy per nucleon in mega electron volt against the mass number of various elements. The binding energy per nucleon first increases with increase in mass number, attains a maximum value and then decreases. Here some noteworthy points are taken into account. He4, C12, O16, etc. have binding energy per nucleon greater than the neighboring elements. These are exceptional cases which will be discussed in later videos. He4, C12, O16, these have nuclear binding energy per nucleon greater than the neighboring elements. Fe56 has the most stable nucleus, and most of the nuclei have binding energy per nucleon about 8 mega electron volt. The lighter elements have lower binding energy per nucleon, as well as the heavier elements also have lower binding energy per nucleons. The lighter elements have a tendency to fuse together, while the heavier elements have a tendency to undergo nuclear fission. These will be discussed in later videos, and this is the reason for very stable nuclide. Some conclusions have been drawn on the basis of this diagram. Iron and nickel have very stable nuclei, and this is why they constitute the core of Earth, which is called Nephe. Ni, nickel, Fe, iron. Iron and nickel are very stable. They have very stable nucleus, and they constitute the core of Earth. The outermost portion of Earth is called Earth crust, followed by Sial, Sima, Nephe, etc. It is the most internal part of Earth, and it is called core, and it constitutes of iron and nickel, and this is why it is called Nephe. The lighter and heavier nuclei are less stable. The nuclei with intermediate masses are more stable, while the lighter and heavier nuclei are less stable. The lighter nuclei have a tendency to undergo nuclear fusion, while the heavier nuclei tend to undergo nuclear fission. About 8 mega electron volt energy is required to remove a nucleon from the nucleus. Most of the nuclei have binding energy per nucleon equal to 8 mega electron volt, and therefore this amount of energy is required to remove a nucleon from the nucleus, which is much greater than, not a smaller, which is much greater than the energy required to remove an electron from an atom, which has value of a few electron volt. About 8 mega electron volt energy is required to remove a nucleon from the nucleus, which is much greater than the energy required to remove an electron from an atom. A few electron volt energy is required to remove an electron from an atom, while 8 mega electron volt energy is required to remove a nucleon from the nucleus. It means the binding energy of nucleon is much greater than the binding energy of electron. Let us illustrate it with the help of diagram. This is He4 atom, and we have already calculated its binding energy per nucleon. If we supply 7.045 mega electron volt energy to the nucleus, this is binding energy per nucleon of this isotope. And if we supply this amount of energy to the nucleus, a nucleon will be ejected from the nucleus. And this is hydrogen atom consisting of one proton and one electron, and the binding energy of this electron is 13.6 electron volt. And if this amount of energy is supplied to this electron will be ejected from the atom, forming H plus ion. Let us compare the amounts of energies, these two. It is mega electron volt, that is 10 to the power 6 electron volt order, while it is of the order of electron volt. It means the binding energy of nucleons is about 10 to the power 6 times greater than the binding energy of electron. Let us see it again. The binding energy of a nucleon is about 10 to the power 6 times greater than the binding energy of electron. Thank you for watching the video with concentration. Please like and share it. If you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.